Hello, this is Teach Nichols, and the topic of this video is closed systems and conservation of energy. The essential question is, how do we track the movement of energy in a closed system? The reason this is such an important critical unit is because energy is conserved. It's one of the 6 variables in our universe that we consider to be conserved properties, and that allows us to solve lots of very different looking problems through these sort of fundamental truths of nature. Reminder that what it means to be conserved is that in any closed system, the total energy, or sigma E, is going to be constant. It turns out it's kind of hard to make a closed system for energy. Unlike mass, where you can break something in pieces and put it in a bucket, you still have all the pieces. Energy has really sneaky ways of getting in and out of systems, because if you wanted to close a system for energy truly, you would have to keep heat and sound and light and anything from escaping from that box, air, right? You can't let anything in or out of the box because everything contains some energy. So in practice, the only truly closed system we can really deal with is the entire universe. And that means that the energy that was in this universe always has been, and we're still kind of cycling through it. That original energy came from the Big Bang, so everything that has energy around us owes that to the Big Bang. Remember that we can draw systems. With a closed system, we would draw with a solid line around it. And you might have a closed system with 10 joules of kinetic energy in it and 20 joules of gravitational energy in it. If you truly could make that a closed system and block out every other kind of energy, you can say that the total energy in that system is 30 joules. Sigma E is 30 joules. If we're dealing with a closed system and you look at that system in a week or a month or a year, we should still have 30 joules of energy into it, but that energy may have transformed or changed from one type to another. So we could have 25 joules of gravitational energy now, and maybe we only have 2 joules of kinetic energy. That means 3 joules has turned into something else, maybe thermal energy. So our system might have totally different kinds of energy than it had before, but we're still going to keep the same amount constant if we're talking about a closed system. So there are 2 ways that energy can move around inside of a closed system. The first is called an energy transformation. In an energy transformation, the energy turns from one kind of energy to another kind of energy while staying in the same system of objects. So for example, in the system of a skydiver, the primary input energy, or energy the skydiver has to start, is gravitational energy. As they fall out of that plane, that turns into motion energy. There's a couple other little minor energies, but those are probably the 2 big ones that are changing. Or in the example of this child in this Zorb in a swimming pool, right? If you consider the entire system to be the child and the ball, then we start off with chemical energy that she has from eating food, and as she sort of runs, that ball spins in place, it turns from her chemical energy into rotational energy of her system as that Zorb essentially spins. So the other way of moving energy around is through an energy transfer. In any system, energy can be traced back to the Big Bang, as I mentioned before. So basically, energy has been moving around from one object to another, or from one type to another, ever since the beginning of the universe. For example, if you wake up in the morning and turn a light on in your room, right, you know that that light has light energy because we can see now. And the lamp is the object that is sort of allowing us to access that energy. Well, that light energy actually came from electrical energy, which is in the wall socket. So that's a transfer from the wall socket to your lamp. That electrical energy here in Oregon primarily comes from motion energy from water moving through a dam. Water basically is falling through this dam and moving, and that is through a process called electromagnetic generation turning into electricity. Where did the water get its movement? Well, we lifted the water really high up and we dropped it, and that's where it got its movement. Really, really high. We lifted it up into the atmosphere. So that water had gravitational energy up in the clouds, and that gravitational energy eventually turns into the motion energy that we can access. Where did the water get its gravitational energy? Well, warm things cause that object to, or cause the water to evaporate from sources of water here on the surface of the earth. So whether that warm thing was you heating up some ramen noodles, or probably more commonly, the sunlight heating up something, that water took that thermal energy and used it to evaporate. So most of the evaporation on Earth occurs from EL, which is sunlight. And of course, we get sunlight from the sun. The sun makes its light energy by having nuclear fission in the core of the sun. So we have this nuclear process happening in the sun, which generates light as its output. How come the sun has nuclear fission? Well, it's because there's actually gravitational energy. We have space dust that is attracted to other space dust, and when it collides into a ball of plasma, a star, right, that gravitational energy and the squishing of the gases all together is what causes the nuclear fission to happen at the core of the sun. Where did the space gas get its gravitational energy? From the Big Bang, right? The Big Bang is, exploded things into a bazillion little pieces spread out all through the universe. It spread out the gas so that gravity could pull it back together again. So ultimately, the Big Bang happened, obviously, so that we can turn on lights in our bedroom. It's very nice of the universe to take care of our things for us so nicely. So along the way, there was a lot of waste energy generated. Waste energy is any kind of energy that was not the primary goal during any transfer or transformation. So in other words, think about all the energy in the Big Bang and the fact that eventually we only got a little bit of light out of it in our bedroom. Everything else along the way was waste energy. That's obviously a very human-centric model of viewing this, to think of everything in the universe just existing to serve our needs. But the power of understanding waste energy is that if we could reduce this waste energy, there would be a lot of energy available for other useful things, like, for example, feeding people in foreign countries, or just saving this energy so that we can have some for our children. So scientists and engineers around the world are working to improve efficiency. Efficiency is essentially reducing the amount of waste energy at any phase in any process so that a larger percentage of the energy makes it through the transformation to become something humans want to use. One of the tools that we use to kind of track the energy transfers and transformations in a system throughout time is the energy bar chart. If we're making an energy bar chart for a closed system, we're going to keep our energy consistent in all of the bar graphs. If it's an open system that the energy values may change. So let's consider a system. This is Jack and Jill, who went up the hill to fetch the pail of water, and then they fell down and broke their crown, and the pail came tumbling after. So the bar graph basically tracks the kinds of energy that are present in the system, or at least the kinds that are changing, the important kinds, as they move through the different moments of time. At the beginning of the climb, before they start going up the hill, Jack and Jill have chemical energy. They've eaten breakfast, and that's the energy that's going to allow them to get up to the hill. So let's say that Jack and Jill start off with 10,000 joules of chemical energy. This is a bit of an estimate at this point, but you could use what we talked about in the last video to make at least an educated guess about how much energy they might have had. Jack and Jill don't have any gravitational energy yet. They don't have any movement yet, and they haven't really created any waste energy. So far, that's the only kind of energy that's in our system is chemical energy, and that means the sigma energy is the same as the value of the chemical energy. Now, once Jack and Jill have reached the top of the hill, the energy looks a little bit different. For starters, we still have 10,000 joules of total energy, and this is because we're considering this to be a closed system. We've got to track all of that energy, so sigma E is going to be constant the entire time. One of the energies that certainly has gone up for Jack and Jill is gravitational energy, because they've climbed up, they're further away from the center of Earth. One of the kinds of energy that's clearly gone down for Jack and Jill is their chemical energy, and this is because they used up energy getting to the top of the hill. They probably didn't actually use up all of the energy that is in them, but it is sometimes useful as a physicist to pick a zero value, so you don't have to do math on numbers that are much different in size or magnitude. So I'm just going to say we'll assume Jack and Jill completely ran out of energy at the top of the hill, and that means they lost 10,000 joules of chemical energy. In addition to the height, the gravitational energy they gained, some of that energy was wasted, right? They probably made some noise as they were climbing, tripping on rocks and whatnot. And they had some thermal energy that was generated as they rubbed on the air, they rubbed on the ground, their shoes collided with things and squished. So those are going to be waste energies because Jack and Jill didn't really want that to happen. They wanted to get to the top of the hill, but they didn't want to waste a lot of their chemical energy along the way. So we do include it in our bar graph, but we're going to put it into a waste energy category or bucket. Then, as Jack and Jill come tumbling down, that energy undergoes another set of transformations. For starters, that gravitational energy that they had at the top of the hill is going to get turned mostly into motion energy because they start moving as they're falling down the hill. So the motion energy goes up, the gravitational energy goes down. In the graph that I've shown, they're not at the bottom of the hill yet, they're kind of in the middle somewhere, so they still do have some gravitational energy, just not as much as they started with. The other thing that goes up is the waste energy. Waste energy always goes up. Okay, this is one of the sad facts about the universe, is that once you create heat or sound or something like that that you're not using, you can't get it back again. It just spreads out, and every new rubbing friction, every new noise that's made is just adding to the noise that you've already made. And so the total quantity of waste is always going to go up until we have no usable energy left in our system. So the tumbling down, we still have some useful motion energy, and we still have a little bit of gravitational energy, but we have a higher percentage of that energy is now being wasted. But you will notice that all three of those energy types still add to 10,000 because we're tracking everything in a closed system. Thanks for watching. Please revisit the essential question, which is how and why does energy move around in systems?